we are trying to find out and write the particle diagrams of what nitrogen would look like as a particle, what hydrogen would look like as a particle, and what ammonia would look like as a particle using the data that Gay-Lussac found in his laboratory. One of the famous things that has done, besides writing hot air balloons, that he actually held the hot air balloon record for altitude. But his most important work is working with gases and gases that react with each other. So he took nitrogen and hydrogen and he made a new gas that had brand new properties. That's why he knew he had a chemical reaction. And he figured out exactly what volume of nitrogen would work with hydrogen to make this new gas. And he came up with about over 100 different reactions with gases. And every one of his reactions, he came up with whole number values. What I mean by that is, this is a 1-to-3 ratio in volume. So you could say this is 1 liter, and all of these boxes are 1 liter, meaning this hydrogen is 3 liters, and that if each box is a liter, all the ammonia is 2 liters. Okay? So when you think about this, you see that 4 liters, okay, of these reactant gases made 2 liters of this new gas, this new chemical formula. You have to understand that we did not know what the chemical formula or what nitrogen looked like as a particle. That's what's fantastic about studying gases, is that we're able to get insights of what atoms look like using gases that were colorless, that we could not see. That's what's terrific about this. So we learn how these chemicals were formed and look like, at least on a model simplistic way, from using gases that we can't see. But we have to understand that in order to do this, we needed another principle. And let me take you through the history. Gay-Lussac in the early 1700s was doing these reactions along with a guy named John Dalton, who was figuring out the modern atomic theory. He suggested that atomos, or atom theory, was the reason how chemical reactions occurred, because one atom was bonding to maybe another atom to make chemical formulas. But they didn't know what they looked like. We couldn't see them. We kind of can see them today. So how did we go about doing this? Well, Gay-Lussac, again, as I said before, and as I've written, has hundreds of reactions, or over 100, I should say, reactions with gases. And he came up with whole number ratios of these gases that were needed to make whole number ratios of these products. There were always whole number ratios. What does this mean? That there must be a whole number ratio of particles. That's great, but we couldn't do anything. We didn't know what these looked like. We had no idea what this was. In fact, chemistry came to a screeching halt, okay, in the middle of the 1800s, because they couldn't come up with chemical formulas that made any sense. We knew these reactions were going. We knew Gay-Lussac's reactions were confirmed and people were doing them. We knew the ratios needed, but we had no idea what the chemical formulas were. Okay, we didn't know the ratio of the different atoms until an important conference in the middle 1800s, and chemistry was almost a science people laughed at, because they couldn't go any further understanding what was happening on the molecular level. Physics was on the forefront, and chemistry was almost laughed at. Okay, until an important conference in the 1850s came about, and they took the work of Gay-Lussac, and a guy named Cannizzaro took the conference by storm and started looking at these reactions. And he brought up a guy that was never heard before, who long since died, and it was Amedeo Avogadro. And it was Avogadro's hypothesis that he used. See, Avogadro was a Italian scientist who long since has passed away in the early 1800s. So published his work in an obscure publication. Remember, this wasn't worldwide net. There wasn't, and when people wrote a book, no one had access to these books unless you traveled to the actual place where they were published. So many people didn't know that Amedeo Avogadro even existed or his hypothesis. But this guy named Cannizzaro at this important conference brought up his work, Amedeo Avogadro's hypothesis, and with that, he was showing people how Gay-Lussac's work was giving us what the atoms, the molecules, or the particles look like. Remember, Avogadro's hypothesis was that a particle could be a single atom, or it could be a group of different atoms bonded together. This was a particle and this was a particle. And what he stated was the same number of particles in a gas under the same conditions of temperature and pressure equaled the same volumes. So with the work of Gay-Lussac, who found out these ratios by volume, combined with the work of Amedeo Avogadro, who again long since passed, nobody knew his work except Cannizzaro, who brought it to the table. He was starting to do this in front of the people's eyes. And this is what we're going to do here. So we have nitrogen. We have no idea what it looks like. We know it's an element. It's made of one form. So let's just make that blue, okay, as a particle of an atom. Then we have hydrogen. Okay, we know it's a lighter gas, so I'll make a smaller symbol, a little round black dot. And these are the only two atoms involved in ammonia. You have nitrogen and hydrogen. You can't create or destroy things. It has to be made of these combinations. So somehow these things were made. We don't know how many. However, the boxes give us a clue. Because these are volumes of gases under the same conditions of temperature and pressure, hello, Amedeo Avogadro's hypothesis, what do I know? Well, I know this, that there are 2 liters of what? 2 liters, 2 volumes, okay, of ammonia compared to nitrogen. What does that tell us? Well, there must be twice the number of particles being made, okay? So let's bring in nitrogen. Let's just make nitrogen 1 particle per box. We can do this any way we'd like. It's a model. So I'm going to put in 1 circle. Okay. Now by putting in 1 circle, okay, if I'm going to make ammonia, well then this is just going to make what? 1 circle here. So if nitrogen was by itself as a monoatomic molecule, as we've talked about, we should only make 1 liter. Same particles, what? Same volume. But notice the volume is twice that of nitrogen. What does that mean? That means we must need another nitrogen. Remember, an ammonia particle is nitrogen and hydrogen. If we have twice the volume, ammonia must be made with 1 nitrogen, at least 1 nitrogen. Since we only have a box or 1 liter of nitrogen, and we have 2 liters of the ammonia, which is made with nitrogen, the 2 boxes are telling me they're twice the number of particles. Well, 1 can't split into 2, so this tells us that nitrogen was diatomic. It bonded to itself, and the chemical formula, party people, is N2. Do you see what we just did there? From this box, and knowing that there was twice the box, remember Amedeo Avogadro's hypothesis, same volume, same number of particles. As long as you understand, a particle could be what? All right, let me just make this, a particle could be what? A pair of atoms or a single atom. In this case, we know ammonia is going to have hydrogen. It's going to build onto this. So this is 1 particle, this is 2. So clearly, we have to understand that nitrogen was N2. Okay, now we're going to make ammonia. What is this telling me? Okay, well, I don't know, but we'll figure it out. Let's start with hydrogen, okay, and let's put down, we can only assume it's made of 1 atom, and let's use black. So since there's 3 boxes, and we're going to say, based on our model, 1 box equals 1 particle. Now that's not true. 1 liter would hold more than 1, but we're just making a model as long as we keep it what? Constant. So I'm going to write 3 of these here. So I have 3 equal atoms. Each particle is 1 liter. Notice this is a bigger particle. It does not matter. one particle, 1 liter, one particle, 1 liter. Now, why am I drawing 3 boxes? We already know from Gay-Lussac's work, it takes 3 liters to 1 liter. So this is something we already know. And from using his work and using Avogadro's hypothesis, we can see some things here. So if I have 3 particles, each particle per 1 box, as we can see right here, this gives us a problem, okay? How do I split 3 atoms to 2 different what? I cannot, okay? So people would say, well, maybe it's diatomic. Now you may say, well, Mr. Grotsky, I don't understand what you're talking about. Well, if I put 1 nitrogen here, I was a hydrogen, and another hydrogen here, maybe ammonia is 1 N to 2 H's, I don't have enough what? H's to make this the same. Okay, ammonia, as we've come to figure out, is a compound. We've learned in earlier modules or chapters that ammonia or a compound has exactly the same properties. Why? Because they have the same chemical formula. So ammonia can have different chemical formulas. So this would make sense if ammonia could have different atoms, but we know that ammonia has the same properties, therefore this can't be the case. So we can't live with that scenario. We have to have 2 particles that are what? Exactly the same. So what we're going to do, and the only thing we can do, is assume maybe hydrogen, just like what? Nitrogen, is also diatomic. So this still is 1 particle. Just because I'm putting another hydrogen here, it's stuck together. It's acting as 1 particle. And I put another hydrogen here, acting as 1 particle. So now I have a total of what? Still have 3 what? Particles. I didn't change that, but I made the particles bigger with more atoms. Again, if you can't see it, this is still works as 1 particle. Same volume, look at that, 1 liter, same number of particles. It doesn't matter if the particle's bigger or smaller. So now if you think with me for a second, how can I put 6 hydrogens on 2 different nitrogens? Well, party people, you're going to put 3 apiece. 1, 2, 3. 1, 2, make that a better circle, and 3. Now what do we have? We have ourselves a formula, NH3. My friends, in chemistry, when Cannizzaro was bringing the boxes in concert with Avogadro's hypothesis into play in the conference, when he started doing this, people were running out of the conference to get to their labs to figure out the chemical formulas of the things they were working on, who could do them the first. So hydrogen was H2. And look at this, party people. Now we know what the chemical formula is. N2 plus H2 made NH3. Now, something really, really important here as we move forward. Okay? Not only did we figure out what they look like using the work with the boxes, we know the chemical amounts of each chemical we need, called the mole ratios. There's going to be 1 and 2 for 3 of these particles. Makes how many of these particles? 2. And that, my friends, is a chemical formula. And when you have a chemical formula, it has to be balanced. Now, what's balance mean? Well, think about this. If I had NH3, and I don't need Gay-Lussac's work to do this, watch what I'm doing. I have N2, I'm going to forget the color coordination at this point, and I have H2. Now, if I know these are the factors at play, I know that there are 2 ends and there's only 1 end, right? All the nitrogens on the reactant side have to equal the nitrogens on the product. So if I've got 2 ends and only have 1 end, I have to throw a 2 here. This 2 is called a mole ratio. It's also called a coefficient. Okay. Now a 2 in front means I have 2 NH3s, right? If I have 2 of these, how many H's do I have altogether? Well, what's 2 times 3? 6, and you can count them. So there's 6 H's. Wait a minute. I only have 2 H's in my written here, so I need a 3 in front. and nothing in front implies 1. If I have an apple, you really have 1 apple. So we can balance these reactions as long as we are confident we know what the chemical formulas were. So what was happening is people ran out of the conference using all the boxes that were done with Gay-Lussac. They were building chemical formulas, and once they had the chemical formulas from the boxes, they could use these for other reactions. So gases led us to the discovery of what the atoms sort of look like. They gave us the chemical formula, able to see what was in these boxes by using colorless gases. So what I was asking you to do was, could you draw these particles? And if you use the same kind of logic, and you had to use Avogadro's hypothesis, you should be able to build that, okay? And write the chemical formula. So it should be this plus this. I should put a plus here, okay? And that is the answer, okay? You can see how rich in concepts all of this is. It's very simplistic, but vital to the total understanding of how chemistry. Now people can do chemistry. Party people, look. They know exactly how much is needed of each what? Reactant to make an exact amount of product. Or if I wanted to make a certain amount of product, I can figure out exactly, I have an ingredients. I have a 1 to 3 to 2 ratio. And this is not a ratio of how many, it's a ratio of how many. There's 1 particle to 3 particles that makes what? 2 bigger particles. And I can use this ingredients to make my chemical reactions. More importantly, explains why the law of combining volume works. Why did the volumes combine? Why did 4 liters become 2? Very simply, because 1, 2, 3, 4 different particles became what? 2 particles. And they're under the same conditions of temperature and pressure. Again, 4 particles, I don't care what the size, became 2. So 4 liters became 2 liters because you cut the number of molecules in half. I hope you grabbed that. Okay?